Here we are going to discuss Wilson's theorem and its applications. Wilson's theorem, Euler's theorem, and Fermat's theorem are three important theorems in number theory which are considered as milestones in the history of number theory. Now, before going to the Wilson's theorem, let us have some observations. We know if Ax is congruent to 1 mod m, the congruence relation has a unique solution if am is equal to 1. This we found earlier. And also this x is assumed the inverse of a modulo m, and it is denoted by a inverse. If you take some example, p is equal to some 7, you can see that the least residues of modulo 7, 1, 2, 3, etc. up to 6 are invertible. We can verify. And not only that, the residues 1 and 6 are self-invertible because 1 into 1 is congruent to 1 mod 7 and 6 into 6 is also congruent to 1 mod 7. And the remaining residues 2, 3, 4, 5 can be paired such that 2 and 4 are inverses to each other and 3 and 5 are inverses to each other because 2 into 4 is congruent to 1 mod 7. 3 into 5 is also congruent to 1 mod 7. Now all the residues of the prime number 7 from 1 to 6 are invertible and 1 and 6 are also invertible. If you take any other prime number, say for example p is equal to 13, then also you can see that the residues modulo 13, 1, 2, 3, etc. up to 12 are such that 1 and 12 are self-invertible, and from 2 to 11 you can pair such a way that each pair, one of them is the inverse of the other. Now if n is any integer, you can see that 1 and n minus 1 are invertible modulo n because 1 square is congruent to 1 mod n for any integer n, and n minus 1 the whole square is also congruent to 1 mod n. So in general, for any congruent relation x square congruent to 1 mod n has actually unique solutions. Two solutions it has at least. One is 1 and the other one is n minus 1. They are self-invertible. So x square congruent to 1 mod n for any integer n has solutions, exactly two solutions, 1 and n minus 1. Now let us go to a result which is a lemma. A positive integer a is self-invertible if and only if a is congruent to plus or minus 1 mod p. So let us try to prove this. First assume that a is self-invertible. Let a be self-invertible. Then we have a square congruent to 1 mod p. That is, p divides a square minus 1, which implies p divides a minus 1 into a plus 1. That means p divides a minus 1 or p divides a plus 1, which can be written as a is congruent to 1 mod p or a is congruent to minus 1 mod p. P divides a minus 1 means a is congruent to 1 mod p. P divides a plus 1 means a is congruent to minus 1 mod p. Combining this, you can write as a is congruent to plus or minus 1 mod p. To prove the converse is also true. Let a congruent to plus 1 mod p or a congruent to minus 1 mod p. In any of these cases, we have to show a is self-invertible. We have one result that if a is congruent to b mod m, then a square is congruent to b square mod m. Using that result here, we can write a square is congruent to 1 square mod p. That is, a square congruent to 1 mod p. It shows a is self-invertible. With the other case, here also a square is congruent to minus 1 square mod p. We get the same a square congruent to 1 mod p, because minus 1 square is 1. So in any of these cases, whether a is congruent to plus 1 mod p or a congruent to minus 1 mod p, we have a square congruent to 1 mod p. That means a is self-invertible. A is self-invertible. So whatever be p, if a is congruent to 1 mod p or minus 1 mod p, a is self-invertible, which shows that the x square congruent to 1 mod p, this congruence relation has exactly two solutions 1 and p minus 1 and p minus 1. So that is what we get from this result. For example, x square congruent to 1 mod 12 or 1 mod 10 has two unique solutions, 1 and 9, because 1 square is congruent to 1 mod 10 and 9 square is also congruent to 1 mod 10. So 1 and 9 are solutions to the congruence relation x square congruent to 1 mod 10. Now, for a prime number, it has certain additional property than this. Suppose p be a prime number, then the residues modulo p from 1 to up to p minus 1 of modulo p are such that we can say 1 and p minus 1 are self-invertible. That is true for any integer. For prime number also it is true. And the remaining residues, that is from 2, 3 to up to p minus 2, can be paired such that each pair is with the property 1 is the inverse of the other. For example, if you take p is equal to say 11, then 1 and 10 are self-invertible and the other residues of modulo 11 are 2, 3, 4, 5, 6, 7, 8, 9. are such that 2 and 6 are invertible, because 2 into 6 is congruent to 1 mod 11. 3 and 4 are inverses, because 3 into 4 is congruent to 1 mod 11. 5 and 9 are inverses, because 5 into 9 is congruent to 1 mod 11. 7 into 8 are inverses. 7 into 8 is also congruent to 1 mod 11. And therefore, the number 10 factorial, which is equal to the product of 1 into 2 into 3 into 4 into 5 into 6, 7, 8, 9 up to 10, can be written like starting with 1 and ending at 10, and the remaining factors can be rearranged such a way that 2 into 6, 3 into 4, 5 into 9, 7 into 8, with the property that each pair in the bracket are inverses. 2 and 6 are inverses, 3 and 4 are inverses likewise. And therefore 2 into 6 is congruent to 1 mod 11, 3 into 4 is congruent to 1 mod 11. We have this result. So this is congruent to 1 into 1 into 1 into 1 into 1 into 10 modulo 11, which is congruent to 10 modulo 11, and this is nothing but minus 1 modulo 11. So here we have taken as 11, it is a prime number, then 10 factorial, that is p minus 1 factorial, is congruent to minus 1 mod p, where p is equal to 11. So this is generalized as Wilson's theorem. So Wilson's theorem says that, so this is the Wilson's theorems. If p is a prime, then p minus 1 factorial is congruent to minus 1 mod p. Let us try to prove this. Let p equal to 2, because that is only even prime number. Then p minus 1 factorial is equal to 1 factorial, which is equal to 1, is clearly congruent to minus 1 mod 2. That is minus 1 mod p. Thus for p is equal to 2, it is very clear that p minus 1 factorial is congruent to minus 1 mod p. Now let p greater than 2. Since p is greater than 2, the residues modulo p are from 1 to etc. up to p minus 1 are having the property that the number 2 to 2, 3 etc. up to p minus 2 can be paired in such a way that each pair, the product, is congruent to 1 modulo p, because in each pair they are inverses to each other, and therefore 2 into 3 and etc. up to p minus 2, that is in some order they are inverses. So 2 into 3, 2, 3, 4 etc. up to p minus 2, among these factors of p minus 1 factorial, each pair is with the property that one number is the inverse of the other. And therefore 2 into 3 into etc. up to p minus 2 is clearly congruent to 1 mod p. And therefore p minus 1 factorial, which is equal to 1 into 2 into 3 into up to etc. p minus 2 into p minus 1 is congruent to 1 into up to this is congruent to 1 mod p. So 1 into p minus 1 mod p. That is congruent to p minus 1 mod p, which is the same as minus 1 mod p. So p minus 1 factorial is congruent to minus 1 mod p. The Wilson's theorem. So it says that if p is any prime number, then p minus 1 factorial is congruent to minus 1 mod p. Now let us do some problem. A problem based on or using this Wilson's theorem. Problem is this. Let p be a prime number and n is any positive integer, then prove that np factorial divided by n factorial into p raised to n is congruent to minus 1 raised to n mod p. So the proof of this wonderful result is that we are using Wilson's theorem. Now by using Wilson's theorem we are getting certain result like this. If a is any positive integer which is congruent to 1 mod p, then the product of integers starting with a plus 1, a plus 2, etc., a plus p minus 2, a plus p minus 2 is congruent to minus 1 mod p. This we can verify. That is, given a is congruent to 1 mod p, therefore a plus 1 is congruent to 1 plus 1 mod p, that is congruent to 2 mod p. Similarly, a plus 2 is congruent to 3 mod p, and so on. A plus p minus 2 is congruent to p minus 1 mod p. Therefore, a into a plus 1 into a plus 2 into etc. a plus p minus 2 is congruent to 1 into two into etc. up to p minus 1 into mod p. That is, p minus 1 factorial is congruent to p minus 1 factorial mod p, but by Wilson's theorem it is congruent to minus 1 mod p. Thus we have the result. If a is any number congruent to 1 mod p, then a into a plus 1 into a plus 2 etc. a plus p minus 2 is congruent to minus 1 mod p. This result actually says that the continuous product or the product of the consecutive numbers between any multiples of p, between p and 2p, or between 1 and p, 2p and 3p, the product if you take, that is congruent to minus 1 mod p. That is 1 into 2 into 3 etc. up to p minus 1. If you take it is congruent to minus 1 mod p. Then from p plus 1. P plus 1 into p plus 2 etc. up to p plus p minus 1. That is 2p minus 1. If you take that is congruent to minus 1 mod p. Similarly, between 2p and 3p, if you take 2p plus 1 into 2p plus 2 plus into etc. 2p plus p minus 1. That is congruent to minus 1 mod p. So, this is the result that we get from this. If a is any number congruent to 1 mod p, then starting with that a up to a plus p minus 2 is congruent to minus 1 mod p. So, this result says that the product of the consecutive integers between any two multiples of p, say 1p, 2p, 2p, 3p, like that, is congruent to minus 1 mod p. Now we are in a position to prove the result np factorial by n factorial variation is congruent to minus 1 raised to n into mod p. So let us take np factorial divided by n factorial into p raised to n, which you can write. Np factorial means 1 into 2 into 3 into up to p minus 1, then it comes p, then goes from p plus 1 to p plus 2, like that, p plus p minus 1, then 2p. Likewise, it goes up to np, the whole divided by n factorial into p raised to n you can write as 1 into 2 into 3 into up to n, then p into p n times. Now you can see that 1 into p is 1p, that cancel with this. So this you can write as 1, 2, 3, etc. p minus 1 as one expression, then into p, then another second expression is p plus 1 into p plus 2, etc. p plus p minus or 2p minus 1, then 2p is there, then again start with the 2p plus 1 and so on, like that. Finally, the last term np comes, divided by, these terms can be combined and written like this: p into 2p into 2p into 3p into etc. np. Now cancelling this p with this p, 2p with this 2p, 3p with the next 3p, like that, all the p, 2p, 3p get cancelled. So remains only 1, 2, 3 etc. p minus 1, then p plus 1, p plus 2, etc. 2p minus 1, etc. etc. Similarly, there will be something like np minus 1, np minus 2 backwards, that bracket will be there. And this is actually a product of n products. We can write like this: pi r is equal to 1 to n, r minus 1 into p plus 1 into r minus 1 into p plus 2, etc. r minus 1 into p plus p minus 1. each bracket is of this type, where r goes from 1 to n. So this is a product of pi r equal to 1 to n this. And each product is actually the product of natural numbers between rp, r minus 1p and rp. Similarly, rp and rp plus 1 like that. And therefore it is congruent to minus 1 mod p using the result that we derived earlier. So it is each product is congruent to minus 1 mod p, and thereby it is congruent to, there are such n product is there. So minus 1 raised to n mod p, hence the result we get. Now the converse of this Wilson's theorem is also true. Actually, Wilson's theorem was proposed by Wilson, but actually it was proved by Lagrange. And he proved its converse also. The theorem is this: if n is a positive integer such that n minus 1 factorial is congruent to minus 1 mod n, then n is a prime number. N is a prime number. Wilson's theorem states that if p is any prime number, then p minus 1 factorial is congruent to minus 1 mod p. If p is any prime number, then p minus 1 factorial is congruent to minus 1 mod p. Now its converse is, if there is any n satisfying n minus 1 factorial is congruent to minus 1 mod n, then n is a prime number. Let us prove this. Suppose n is not a prime number and n minus 1 factorial is congruent to minus 1 mod n. So let n be positive integer such that n minus 1 factorial is congruent to minus 1 mod n, and assume n is composite. That means n is equal to some AB, A into B, where A and B are such that integers between 1 and n. Now, since n is equal to AB, n divides A. And also, since by hypothesis n minus 1 factorial congruent to minus 1 mod n, by 1, n divides n minus 1 factorial plus 1. Since n minus 1 factorial is congruent to minus 1 mod n divides n minus 1 factorial plus 1. Now since n is A is such that it is in between 1 and n, since A is such that 1 less than A less than n, A can be 2, 3 up to n minus 1, any one of these integers. And therefore, A divides n minus 1 factorial, because n minus 1 factorial is the product of the integers 1, 2, 3, etc. up to n minus 1. So A is a number in between 1 and n. Therefore, A can be 2, 3 or n minus 1. Therefore, A divides n minus 1 factorial. Now, since n divides A and n divides A divides n. A divides n because n is equal to AB, so A divides n. Since A divides n and n divides n minus 1 factorial plus 1, using 2 and 3, A divides n minus 1 factorial plus 1. And therefore, making use of 4 and 5, A divides n minus 1 factorial and A divides n minus 1 factorial plus 1. Therefore, A divides n minus 1 factorial plus 1 minus of n minus 1 factorial. That is, A divides 1, which implies A equal to 1, which is a contradiction. Because here A is assumed, or A is such that 1 less than A less than n. Here we got A is equal to 1, so which is a contradiction, and therefore we cannot write n is equal to AB, that is n is prime. Therefore n is prime. So combining Wilson's theorem and its converse, it can be stated like this. If n is any integer such that n minus 1 factorial is congruent to minus 1 mod n, if and only if n is a prime number. Whereas n is a prime number if and only if n minus 1 factorial is congruent to minus 1 mod n. So this result could be used for checking a number is prime or not. Because if it is a prime number, then it satisfies the Wilson's condition, n minus 1 factorial is congruent to minus 1 mod n. But unfortunately, this has no applicability because computing n minus 1 factorial is very difficult when n is very large. Now, let us take some problems from exercise part. The first problem is, find the self-invertible modulo 90. Self-invertible modulo 90. We know the residues of modulo 19 are from 1 to up to 18. Of course, 0 is there, but we are taking 1 to 18, of which we know 1 and 18 are self-invertible. So, the self-invertible modulo 19 are 1 and 18, since 1 is congruent to, 1 into 1 is congruent to 1 mod 18, 1 mod 19, and 18 into 18 is also congruent to 1 mod 19. We can verify. Another problem is, solve the congruence equation, congruence relation. X square congruent to 1 mod, say 12, mod 12. We know x square congruent to 1 mod 12 means that x is self-invertible. Here the modulus is 12, and we know we have the result that 1 and 11 are self-invertible modulo 12, because 1 into 1 is congruent to 1 mod 12. 11 into 11 is also congruent to 1 mod 12, because 11 and 11 is 121 minus 1, 120 is a multiple of 12. And therefore, x square is congruent to 1 mod 12 has exactly two solutions, 1 and 11. 1 and 11. Now, another problem without using Wilson's theorem. Verify that p minus 1 factorial is congruent to minus 1 mod p for p equal to say 7 or 30, whatever it is, let me 7. We know p minus 1 factorial is 6 factorial, which is 1 into 2 into 3 into 4 into 5 into 6. Here 1 and 6 are residues modulo 7, which are self-invertible. 2, 3, 4, 5, these residues modulo 7 are pairwise inverses, because 2 into 4 is congruent to 1 mod 7, 3 into 5 is congruent to 1 mod 7, and therefore this is congruent to 1 into, by pairing like 2 into, this equal to, actually first you can write equal to 2 into 4, 3 into 5 into 6 is congruent to 1 into 1 into 1 into 6 modulo 7, which is equal to 6, which is congruent to 6 mod 7, and it is same as congruent to minus 1 mod 7. Thus, for p equal to 7, we have 6 factorial is congruent to minus 1 mod 7, which is Wilson's theorem. Now, another problem. If p is a prime number, prime, so that p minus 1 into p minus 2 into etc. p minus k is congruent to minus 1 raised to k into k factorial into mod p. Proof. Given p is a prime number, therefore p minus 1 is congruent to minus 1 mod p. Yes. P minus 1 is congruent to minus 1 mod p. Actually, this is true for any number. P need not be prime. If p is any number. Any number. P minus 1 is congruent to minus 1 mod p. So p minus 2 is congruent to minus 2 mod p. And so on. P minus k is congruent to minus k mod p. And therefore, p minus 1 into p minus 2 into etc. p minus k is congruent to minus 1 into minus 2 into etc. minus k mod p, which is minus 1 raised to k. There are such k minus 1 and 1 into 2 into etc. k mod p, which is congruent to minus 1 raised to k, k factorial, 1 to etc. k is k factorial mod p. That is the result.